Okay, so sorry for the late start here. It just took a little bit of technical difficulties, but I think we're off and running now. Okay, so my plan for the evening is to, of course, try and go through these problems that are on the final exam review session sheet. There's 11 of them here, and they obviously don't cover everything, but try and hit a bunch of different things. Focus on some old stuff, some new stuff. I'm going to jump around on this review session sheet again. And if you have to leave early or you just don't want to worry about taking perfect notes, you can always go look at the solutions later because those are posted as well. But anyway, I mean, my advice, I would say, for the final is to just think of it in the 3 chunks that we took the midterms on. So the first chunk was the first 3 chapters. So you can go back and look at that again. The first 3 chapters, would be, first 3 chapters would be on the differential equations, first order differential equations. So chapters 1 through 3, first order differential equations. So we have, what are the things you need to be able to do there? Well, you just need to be able to deal with the 4 main types of differential equations that we learned how to solve, right? Which would be the separable, what are the other ones? Bernoulli, homogeneous, and linear. So I'm going to put that next. Linear, Bernoulli, and homogeneous. And I think you should go back to the review packets for those exams to kind of remember what are the important things to remember from these different topics. So you need to know, for example, the form of a linear differential equation. Basically, it's y prime plus p of x y equals q of x. So that's the form of a first order linear equation. And in order to solve such an equation, you have to use the integrating factor. So that was the I of x that we introduced way back, like the beginning of the semester. So this thing is e to the integral of p of x dx. Okay, so the integrating factor is the trick to doing this. And once you find the integrating factor, which you don't need a plus c for on the integration, by the way. Once you find the integrating factor, you basically multiply the differential equation through by that integrating factor. When you do that, the right-hand side of the equation just becomes q times I. And when you multiply through by I on the left side of the equation, what you get is the derivative of I times y. That's as a product derivative. So it's the derivative of that product. So this is how you're going to solve for y. You're basically going to write down this expression, integrate both sides, and then divide by the integrating factor. So that's the secret to that. Okay. So these are the main equations that you need to know for the for the linear differential equations. Okay, there really aren't any equations for the separable ones. So this is for linear. Now for Bernoulli, the Bernoulli question.
Before we move away from linear, when you integrate, you have to add c, right?
Down here you do. On the bottom integration, when you integrate q times I, you will need to add a plus c, but not on the integrating factor itself.
Yeah, no, I just remember when we get to the iy prime equals qy, you get to the solution and it looks really simple, and then you remember you have to add the plus c.
Right. The plus c, it's not that you're adding the plus c right way at the end of the whole problem.
Mm-hmm.
You're adding the plus c the moment you do this integration.
Yes.
Okay, great. And then other things might happen to it, because after you add the plus c here, you might, in order to solve for y, you might have to exponentiate, which turns addition into multiplication. Right? We've seen some of the algebra of that quite often, of the sort of things you need to be able to do. You might need to remove absolute value bars. We've had to do that a few times, and so on and so forth. Okay? Now, the Bernoulli equation is almost the same thing, and I tricked a few people on yesterday's group work into thinking there was a Bernoulli equation in that list of 6 things, but there wasn't. Basically, the difference here is the y to the n that shows up on the right-hand side of the equation. The y to the n that shows up there. Now, the things you need to be able to do here is you have to be able to identify a Bernoulli equation, like look at it and tell me it's Bernoulli. Then you need to know what to do if it is Bernoulli, and there's two formulas that you have to know. The first one is that u, which is the change of variables that you're going to use, is equal to y to the 1 minus n. So you need to know how the y variable gets changed when you turn it into u. And then, equally important to that, you need to know what the new equation is after you change the variables. You don't want to have to derive it during the test, right? You want to be able to just write it down. I mean, you could derive it. You could derive it by basically solving this for y, taking its derivative and plugging the results in for y everywhere you see a y, but you don't want to have to go through that. So instead of having to derive it, it's nice to just know it. And here's what the formula becomes. U prime plus 1 minus n times p of x times u equals 1 minus n times q of x. Okay, so this is the formula that you end up with. 1 minus n, of course, is just a constant number. And the difference now is there's no power of any unknown function on the right-hand side. It's just 1 minus n times q of x. So what you have now is linear. In other words, Bernoulli equations always become linear when you apply the change of variables. Bernoulli equations always become linear. Okay? And then you can solve it like a linear problem. I like asking Bernoulli equations because it allows me to test not only your ability to do a change of variables, but also how to do the linear equations too, because it turns into a linear equation. So make sure you're comfortable with the Bernoulli equations. Okay? And then finally, the homogeneous ones. I'm running out of room here. Just throw it off to the side here. The homogeneous ones are just the ones where you solved for y prime and you have some function of x and y, and it's a function of x and y where anytime you put a t next to x and next to y, everywhere you see an x and everywhere you see a y, as many times as you see those variables, you stack t's next to the x's and y's. If those t's all cancel right back out again, then it's a homogeneous differential equation. Does anybody remember the change of variables for a homogeneous differential equation? It was on the group work we did yesterday for any of you who might have tried that.
Y equals vt?
There's no t in it. We usually
Or
use
vx?
Yes, it's y equals xv. This is the change of variables that you need for that. Okay? And so then, of course, you're also going to need to know what y prime is, and you can just use the product rule to write down what y prime is. It'll be x times v prime plus v. So these two formulas basically govern the homogeneous differential equations. And after you apply that change of variables, the differential equation that you end up with, after you do it, is always separable. So after you apply y equals xv, you're going to end up with a separable problem. Okay? So Bernoulli equations become linear, homogeneous equations become separable. Right. Does that make sense? So this is the idea of change of variables here. Now, I could ask you to solve a first order differential equation that was none of these four types, but if I did that, I would have to tell you how to approach it. Right? In other words, the only ones that I've ever taught you directly in class are these four types. It doesn't mean that I'm afraid to ask you anything else. It's just that if I did, I would not be assuming you know how to solve it, and therefore I would have to tell you, like maybe there would be a different change of variables that you would need to apply in order to solve it. So I could ask you something like that, but more than likely, I mean, these are obviously the ones that we've talked the most about. Other than that, the only other thing in Chapter 1 is that I think you should be comfortable with are the Newton's law of cooling. And the mixing problems. So those are like the applications. right? Newton's law of cooling is a nice application of a separable differential equation. And the mixing problems, that's the tank with the chemicals in it. And I'm only going to ask you a problem with one tank if I do. It won't be the two-tank thing I was alluding to yesterday. So the mixing problems are always linear, first-order linear differential equations. So these are just applications of the differential equations we've talked about above. I'll give you the differential equation for mixing problems. For the problems about Newton's law of cooling, you just need to remember what the differential equation is. So the rate of change of the temperature as a function of time is just negatively proportional to the difference between the temperature of the object and the temperature of the medium. So just good to know this one. And you should be able to solve this. You should be able to take this and separate the variables here are the little t and the big T. So you should be able to get all of the big T's on one side, all of the little t's on the other side. It's separable, and then just integrate both sides. Okay, so all of this is kind of chapter 1, a review of chapter 1 right here. Okay, everybody all right with that? As far as chapter 2 goes, so actually a lot of the formulas you need to review are here. As we go into these later, talking about some of the things in the later chapters, there's going to be less formulas that we have to talk about. I'm not going to talk about as many formulas because there aren't as many. So in chapter 2, you just need, what are the sorts of things you need to be able to do in chapter 2? Well, you need to be able to do matrix algebra. Now, I'm probably not just going to give you 2 matrices and say, oh, please add these together, or please multiply them, or anything like that. More likely, those types of calculations will be embedded in another problem. Such as when you do the defective linear systems in chapter 7, you have to take A minus lambda I and square it and cube it. Well, that's doing matrix algebra, right? So things like adding, subtracting, multiplying matrices, scalar multiplying matrices, all of those things. And also transpose. So, basically addition, subtraction, multiplication, transpose, right as a power of t. Just being able to work with things like that. And some properties, some of the properties that we need to know. So for example, remember that when you transpose a product, if I take A times B and I transpose it, well, that's the same as B transpose A transpose. So the order of the matrices gets reversed. And there's an exactly the same thing for inverses. Oh, I should add inverses to my matrix algebra list up here. So -1 exponents. So A, B inverse, well, that's just B inverse, A inverse, right? So things of that nature you're going to want to be familiar with. Of course, you're going to need to be able to do Gaussian elimination. You're going to need to be able to, which involves, of course, EROs. So EROs and pivots, free variables, all that stuff. But see, you don't need to spend massive amounts of time reviewing that because you have been doing that all along in the recent chapters, right? That's not so new. So stuff like that. Finding inverses. So finding A inverse. We have 2 methods for doing that, and one of them is in chapter 2, and one of them is in chapter 3. There's the one way of doing it is where you put the matrix A here, and you write the identity matrix next to it. Remember this? And then you do the EROs, and you try to get the identity matrix on the left side of that bar. And if you're successful, then the matrix at that same moment that appears to the right of that bar is A inverse. So this is called remember, this is the Gauss-Jordan method. That's the Gauss-Jordan method. So, that's really just EROs. It's a lot of busy work, really. There's also a way of finding A inverse that we learned in chapter 3 using determinants, but I'll come back to that in a second. Okay, so there's that. Trying to think what else in chapter 2. That's really the highlights of chapter 2, I think. And then chapter 3, well, I guess one other thing. Make sure you know the formula. We used it yesterday, so it might be fairly fresh. The inverse for a 2x2 matrix. This is just a nice formula to remember. You take 1 over the determinant of that 2x2, which would be AB minus BC. And then the matrix that it is multiplied by, we simply reverse the positions of the A and the B. And we put minus signs on the off-diagonal entries B and C. So A and D get swapped, and B and C pick up minus sign. Okay, so that's a good thing to be familiar with in chapter 2 as well. Feel free to speak out if there's like anything, it's like, oh, he forgot to say something, or there just feels like there's a topic missing here. That's always possible. I guess another thing I didn't talk about, it's kind of related to pivots, would be the rank of the matrix. So that's something we learned about in chapter 2. It's just the number of pivots that are in the row echelon form. But of course we came back to that later as well, right? Because later on in the semester we had the rank nullity theorem. So the rank was the number of pivots, the nullity was the number of non-pivoted columns, and together that adds up to the total number of columns of any matrix, which is usually called N. Right, okay, so that's coming up later. Chapter 3, of course, is determinants. So you should be able to find determinants, of course. Pretty much do it every single day for the last month in this class, because every time you try to find eigenvalues of a matrix, you're taking a determinant, right? Comes up a lot. So finding the determinant, of course, we have like an arrow method for a 3x3 matrix. We also have cofactor expansion. And then the other thing we can do is we can row reduce the matrix and get some zeros into the matrix by doing that, so that your matrix has a simple cofactor expansion. Or possibly, remember, if the matrix is upper triangular, then the determinant is, how do you calculate the determinant if it's upper triangular?
It's just the trace.
Yeah, you just multiply the diagonal entries. Yeah, you just multiply the diagonal entries, and that's it. So it's easy. You just have to remember how the EROs that you used to make the matrix upper triangular, how those EROs affect the determinant. So I'll call that properties of the determinant. So properties of the determinant of the matrix. So, you know, what am I talking about there? Well, I'm talking about things like if you switch 2 rows, the determinant picks up a minus sign. If you add a multiple of one row to another row, no change. If you multiply a row through by a constant, then the determinant multiplies by that same constant. Okay, so those are your EROs. And then there's other things. So you can transpose the matrix, right? The transpose, remember, doesn't do anything to the determinant. What else have we learned about determinants? Determinants respect multiplication. So the determinant of AB is the same as determinant of A times determinant of B, but they do not respect addition. So I can write down 2 matrices A and B that have a sum, and the determinant of the sum of those matrices isn't always going to be the same as the sum of the individual determinants. Right? Yeah, right?
Sorry to stop you, but for cofactor expansion, will that work for any size matrix? Or is it just
No, that works for any size. Yeah, cofactor expansion works for any size matrix. We actually did, I think in class we might have even done a 4x4 at some point. Exactly. But once you're getting to like a 4x4 matrix and there's not a lot of zeros in it, you aren't going to want to do cofactor expansion straight off, because it's going to take you a long time to go across a row or a column. So you can also combine these methods together. So if I ask you a pretty big matrix and I say, what's the determinant here? Right? You could say, well, I don't want to cofactor expand it the way it is right now, but I'm going to do a few EROs first to get some zeros into it to kind of reduce the size of the problem I have. So you can go a partial ERO reduction using these properties, and then you can say, all right, now I've gotten enough zeros on a particular row or column that I'm comfortable expanding that row or column, and then use the cofactor expansion. So you're not resigned to only using one of the methods. You can kind of use them together. Okay? But anyway, you want to know all these properties of determinants. That's a kind of a big deal. And that's really, for the most part, that's what chapter 3 is. Okay, so finding the determinant of A, of course, cofactor expansion. But again, you guys, you do this all the time. This is not anything too bizarre. So since you do it all the time, it hardly needs a whole long review. Okay, so now I'll just say a couple quick words about, I guess just chapter 4. I'm not going to go over a review of chapters 5, 6, and 7 because we just did that last week in the review session. So I'll just say a couple quick things about chapter 4, and then I want to move into these problems ASAP so we have plenty of time to work on them. And then you guys can just go back and review the previous review sessions about the stuff that we just covered recently. Renee.
So in chapter 3, adjoint method and Cramer Rule.
Oh, I forgot all about that. Thank you. That's why I'm glad you guys are speaking up. Yes, you want to know that because I talked about finding A inverse. So there's the adjoint method. Thank you. A inverse is 1 over the determinant of A times the adjoint of A. Oh yes, for sure. That's good to know. All right. So the adjoint, remember, is just the matrix of cofactors transposed. So you go through, you find the matrix of cofactors, and then you transpose that matrix. That's the adjoint, and then you divide by the determinant. This is a good method for finding A inverse because the fractions that are out that might show up in the inverse are sort of factored out, right? Because this denominator of determinant of A is outside of the adjoint. So given a choice, usually I prefer the adjoint method for finding A inverse actually compared to the Gauss-Jordan method, just because EROs can be tedious. So that's definitely the case. And then the Cramer's rule, just quickly say something about that. I mean, these are important things. I mean, you guys use these in engineering a lot, so it's important for me to mention this. So Cramer's rule is where you want to solve one of these systems, and you're in the case where the matrix A is invertible. So you have Cramer's rule only works if it's a nice square system with an invertible coefficient matrix A. But Cramer's rule basically gives you a formula for X. What you basically do is, all right, just remind you how this works. So if X is a column, let's say X1, X2, up to Xn, and I want to solve for X, then the way you do that is you find each entry of it by a formula. So the kth entry of this unknown vector X, the way you do it is, well, on the bottom you take the determinant of the matrix A. And then on the top you take the determinant of the matrix that is usually called B sub k. And the B sub k, this is the matrix where the kth column of A is replaced by the vector B. So, I'm going to spend a lot of time on this, but I mean it is a nice handy way of determining the solution to a problem like this here. So basically what you do is you take the matrix A, you take out one of the columns and replace it with the B vector instead and find the determinant of that. And then divide that by the determinant of A. That's going to tell you the kth entry of the unknown vector. I don't think I actually derived that in class, but I certainly, we certainly have have looked at this through a couple of examples. It hasn't been a big thing, but it is worth mentioning. Okay. Everybody all right on that? So the first midterm was those first 3 chapters, basically, which we've kind of looked at now. The second midterm was mostly just chapter 4, that really long chapter. So let me very briefly, I really don't want to spend long on this, but I just want to remind you what's in chapter 4, which is the longest chapter of the book, so that, I don't want to review everything in detail, but just get some things down so you might jog your memory about something that you need to review. Okay, so the first thing is you have the vector space axioms. The main axioms that you need to worry about, I probably won't ask you to verify a lot of these axioms, but there's a couple of things that you do want to know about for sure. One of them is the zero vector axiom, because when we're looking at subsets and asking do they form a vector space, a lot of times the first thing we do is check the zero vector. Is it in the set? So the zero vector is an important one. And then the other axioms that are the most important, of course, are the closure under addition and the closure under scalar multiplication, the first 2 axioms. Okay, so these are the most important axioms, because when we get to subspaces, here's the next section, subspaces have to be closed under addition and scalar multiplication. Excuse me. Okay, so does that make sense? Checking whether things are subspaces or not is something we've done a lot of. Remember, the things we've spent lots of time on are the things you want to spend time reviewing. So to check if something's a subspace, I usually start real quick, is my zero vector there? If not, then we're done. We can just say, nope, it's not a subspace. So we move on. If the zero vector is there, then we go through the process of checking the closure under addition and scalar multiplication. It may or may not be a subspace in that case. Okay, and you don't have to, so that's like a yes-no question. Is this a subspace? You don't have to see the answer in your head necessarily ahead of time. I mean, it's okay to sort of take it step by step. First check the zero vector, and then check each one of these one by one and see if you can write down a justification or find a counterexample. Okay, so subspaces is a good deal. One very popular way of making a subspace is to take the span of anything. That's always a subspace. You're taking all of the linear combinations of whatever the vectors are that are inside of those squiggly braces. Okay, so that's a classic way of creating a subspace automatically. Of course, what we really want to do is span V. V is like a vector space. We're looking for a spanning set. So a lot of times the goal in this vector space material is find a basis for V. So we do this a lot, right? And so probably the concept of a basis would be like one of the cornerstone, most central, important things in linear algebra. Pretty much guarantee that there's going to be something about this on the test for sure, because this is the core of everything. Basis, of course, is also tied in with dimension. So if I can find a basis for V, then I can also talk about the dimension of V. And that's related, of course, just the number of vectors that are in the basis. Okay, so that's a key concept. So you're really looking for a spanning set, which is Li, right? A spanning set that is linearly independent. That's kind of the key. Those two components. If I have a spanning set, but it's not linearly independent, then what you want to be able to do is reduce it to a linearly independent set. Remember how we do that? We take the vectors that are in our spanning set, line them up in the column